So, it's past 12, so good afternoon to all. Believe me, it's very hard for me to stand up here, after all these great speakers. Allow me to introduce myself. My name is Uros Milovancevic. I come from Faculty of Mechanical Engineering, University of Belgrade. Today, I'm going to talk about some part of my PhD thesis, named Performance Investigation of Tube Air Cooler. The content is shown in this slide. First one is introduction, short introduction, then something about air cooling coils. The third is experimental setup and measurements, and at last we're going to hear conclusion. First one, fin and tube heat exchangers are, as we all know, very commonly used in heating, air conditioning, and refrigeration purposes in petrochemical, chemical, food industries, so in other fields. In technical practice, it is very often case to find cooling and dehumidifying of humid gas. Such cases are cooling humid air in refrigeration plants, cooling of exhaust gases in thermal power plants, cooling of various gases in some other process industries. What was the aim of this whole research? Well, the aim was to make a software solution that would be able in practice to provide fast and reliable results in calculation of this type of heat exchangers. In this picture, we can see the schematic preview, cooling and dehumidifying surface with index 1. It is marked the hot fluid, in this case it was airstream. With index 2, it is marked the cold fluid, which is water. And indexes I and O are respectively inlet and outlet of the section. Below the figure, we can see the well-known heat balance equation. In this picture, we see the tabulated values with geometrical parameters of tested air coils. It was tested two different arrangements of air coils. One arrangement was with two exactly same type of heat exchanger with series connection from the air side and parallel connection from the water side. And the second configuration was testing of only one heat exchanger, where the other one was dismantled from the installation. So we can see here 4 rows of tubes and 8 rows of tubes, giving the total of 48 and 96 tubes with with first and second configuration. So I will stick with this one for a bit longer. At the upper part of the picture, we see the open air tunnel, which was used for testing the air coolers. At the left upper part, we see the intake device. It was plastic tube, which was used to measure volumetric flow rate of the air. Actually, it was measured the pressure drop at the entrance of the plastic pipe. After, we can see this fan, and with frequency regulator, it was varied the air volume flow rate. This is the heat exchanger section. In front of the section, there were established measuring points for parameters of air, such as dry bulb temperature and relative humidity. And at the outlet, I'm sorry, do you see the mouse pointer I'm trying to show here? Probably it's, oh, sorry, I thought you can see the mouse pointer. So this is the inlet device, fan, as you can see, and heat exchanger section. Section with measurement points of the inlet air parameters, and of course outlet parameters of air was measured at the outlet section of heat exchangers. Of course, it was measured pressure drop across the heat exchangers, and below the heat exchangers there was drainage plate with the drainage pipe and siphon, where the condensate flow rate was measured. Also, the temperature of the condensate was measured using PT100 probe. The cold was induced in the heat exchangers from the secondary circuit with cold water, and water was cooled in the primary evaporator. From the primary refrigeration machine, it was chiller with zeotropic blend 407C. Volumetric flow rate of water was measured at balancing regulating valve, and also it was used 3 steps circulating pump. Okay, here we can see some photos from the field testing. Upper left, the chiller. Upper right, you can see the open air tunnel. Down here, here is the tested heat exchanger. And here we can see also the air tunnel with the mounted measuring equipment. Shortly, this is the refrigeration characteristic of used chiller, and it was defined for about 12 kilowatts in nominal regime. After the measurements was conducted, the statistical analysis was performed, and here are the well-known equations used for calculating heat exchanger duty for the air side, using the, of course, pressure difference, enthalpy difference. After the heat duty for the air side, it is calculated water side heat duty using the temperature difference, and then the mean value of heat duty was calculated as arithmetic value. For each working regime, unsteadiness or heat balance dispersion is calculated using this formula, and in literature it is found that acceptable level of error is between 3 to 7%, even 10. So all regimes within error of 10% were adopted as acceptable for further analysis. Also, this expression was used for temperature difference as mean logarithmic temperature difference, and correction factor for temperature difference is adopted as 1, because it was shown for the performed and collected measurements that the error was less than 2.5%. The measured overall heat transfer coefficient is calculated as the ratio of mean value of heat duty and, of course, surface and delta T. From the other hand, as we can see up here, this is well-known expression for overall heat transfer coefficient calculated for the air side, where we wanted to calculate alpha 1, which is the heat transfer coefficient for the air side. Of course, for the water side, heat transfer coefficient is calculated using this expression and Nusselt correlations, equations for laminar and turbulent flow. So I have passed to conclusion, and the question is whether the available literature sources are related only to the specific product and construction of some heat exchanger, or is there some analysis with the generally applicable conclusion that may apply at the same time a number of other constructions? And the following results within this research were achieved. It was made, or should I say designed, an experimental installation for testing hydraulic and thermal performances. There were confirmed correlations for calculating pressure drop and heat transfer coefficients in dry regimes, without moisture condensation. Also, there were determined and confirmed correlations for calculating pressure drop in regimes with moisture condensation. And finally, the main goal, it was defined the improved calculation method for determining heat duty and condensate flow rate for, of course, wet regimes, and of course, only heat duty for the dry regimes. That's all for me. Thank you very much for your attention.